If you're looking for a short primer on AI so that you can appear informed, intelligent, and cut through the hype, this is the place for you. This briefing covers the scaling laws in the performance of large language models, LLMs, the technology driving the development of tools like Gemini, ChatGPT, Claude, and Grok over the past few years. It will explain what they are and where their limits might be, so you can show your credibility as an AI-informed leader. It also includes links to external references you can use to back up what you say if you need to. So, let's go. At their core, AI scaling laws describe the predictable relationship between the performance of an AI model and the resources invested in it. Things like the amount of training data, the number of model parameters, and the computational power used. Think of it like this. If you add more ingredients to a recipe, you generally get a bigger cake. In AI, these recipes often show remarkably consistent improvements in performance as you scale up their inputs. For LLMs, a seminal paper is Scaling Laws for Neural Language Models, 2020, by Kaplan et al. From OpenAI, which really brought these relationships to the forefront. This paper highlighted different types of scaling laws. Data scaling laws, how performance improves with more training data. Parameter scaling laws, how performance improves with more parameters in the model, i.e., making it bigger. Compute scaling laws, how performance improves with more computational power. These scaling laws are power law relationships, meaning performance increases proportionally to a power of the scaling factor rather than linearly. For large language models, these scaling laws have been a game changer. They indicate that simply making models bigger with more data and compute will lead to better performance. And that is precisely what has been observed until relatively recently. This discovery has in turn given Frontier Labs the confidence to spend huge sums on LLM development, which has in turn driven the rapid advancements we've seen in AI boom. However, while scaling has delivered incredible gains, it's not a magic bullet. There are diminishing returns. Each incremental improvement requires significantly more resources, raising questions about sustainability. Are we just making bigger models, or fundamentally smarter ones? There's also no guarantee that scaling laws will continue to hold. They are not physical laws, just observations whose trajectories could change. As the availability of new training data decreases, we've already seen AI labs change approach. While models continue to scale, there is an increasing focus on compute-optimal approaches, ones that achieve high performance with less compute through more efficient architectures or new training techniques. We are also seeing more focus on smaller models that are highly effective for specific tasks rather than a single, monolithic super AI. So, while scaling laws have been foundational to the AI revolution, they have limitations and there is no guarantee they will continue. If anyone tells you otherwise, make sure you challenge them.